Welcome to the Explainer. You know, we spend a lot of time looking at heat moving in a straight line, but let's be real, that's not how the actual world works, right? Today we're stepping out of that one-dimensional bubble and taking on multi-dimensional steady-state conduction. It's going to be fun.
Think about it. In reality, heat doesn't just politely march down a single straight path. No way. It spreads out. It radiates through corners, wraps around buried pipes, and just generally flows everywhere all at once. So the big question we're tackling today is, how do we actually calculate heat transfer when it's moving in 2 or 3 dimensions simultaneously? Let's dive right in. Here's the roadmap for today. We'll start with heat in multiple dimensions, move into the exact mathematical approach, look at graphical analysis of heat, explore shape factors, run through some practical shape factor examples, and wrap up with finite differences, our numerical methods.
All right, part 1, heat in multiple dimensions.
So when we analyze steady-state heat flow in 2D using the Laplace equation, we're looking at temperature gradients in both the x and y coordinates. Check out how the heat moves in both directions here. The total heat flow at any given point, it's just the resultant vector of those two flows. But here's the absolutely crucial part. This total heat flow vector is always exactly perpendicular to the constant temperature lines, which we call isotherms. Basically, if you can map the temperature distribution, you've got the precise direction of the heat flow. Moving on to part 2, the exact mathematical approach. Okay, so to solve that Laplace equation analytically, we really have to break out the heavy calculus, like the separation of variables method. Take a look at this rectangular plate. We've got 3 sides at a constant temperature, but the top edge has this sine wave temperature distribution. When we apply our boundary conditions, we end up with an infinite series solution. Visually, it's actually kind of beautiful. You get these complex intersecting isotherms and heat flow lines, but actually calculating the exact temperature at any specific coordinate, yeah, that involves a massive, unwieldy equation.
And hey, if the phrase infinite series math just made your head spin a little bit, you're not alone. Our source material actually calls this out directly, saying analytical solutions are not always possible to obtain. Indeed, in many instances, they are very cumbersome and difficult to use. So engineers desperately needed a more practical way forward. You know, a way to solve real-world problems without spending weeks doing calculus.
Which brings us to section 3, graphical analysis of heat.
Well, before we had modern computers to do all that heavy lifting for us, engineers came up with a really clever workaround. They would literally sketch the heat flow by hand. They built groupings of what are known as curvilinear squares, carefully drawing lines so the x and y increments were roughly equal and perpendicular to each other. This created a grid of isotherms and heat flow lanes. Think of it like a highway, right? But instead of cars, it's heat transferring from a hot inner surface to a cold outer one. If you count up the number of lanes and divide by the temperature increments, you get a ratio to estimate the total heat transfer. Now, obviously, it relied a lot on the skill of whoever was drawing it, but honestly, what a brilliant historical stepping stone.
All right, section 4, shape factors, engineering shortcuts.
So if analytical math is exhausting and hand drawing is super tedious, this right here is the ultimate engineering cheat code. For a multidimensional system with just 2 temperature limits, engineers managed to compile all that intense geometry and calculus into a single variable, the conduction shape factor. We just call it S. Instead of pages of infinite series, your total heat transfer equation boils down to this: Q equals K times S times the overall temperature difference. You're literally just multiplying the material's thermal conductivity, the geometric shape factor, and the delta T. It's brilliant.
And here is the absolute best part. These shape factors, they are already pre-calculated for a massive variety of standard physical systems. On the left, there's a horizontal cylinder buried in a semi-infinite medium, which is perfect if you're trying to figure out heat loss from an underground pipe. On the right, totally different geometry, a buried cube. Our source gives us a huge table packed with specific algebraic formulas to find S for both of these, plus buried spheres, parallel disks, eccentric cylinders, you name it. It takes these insanely complex multidimensional fields and turns them into plug-and-play algebra.
Let's look at section 5, practical shape factor examples. Let's actually see this shortcut in action with a real-world scenario. Imagine a 3D cubicle furnace made of fireclane brick. Let's say it's 50 centimeters cubed on the inside, with 10 centimeter thick walls. The inside is blazing hot at 500 degrees Celsius, and the outside is sitting at 50 degrees. To figure out the heat loss, we just break this 3D shape down into its components using different shape factors.
Step 1. Calculate the shape factor for the area of the 6 walls. Step 2. Use a slightly different formula for the 12 edges. Step 3. Calculate the 8 corners. And Step 4. Just add them all up. For this specific furnace, that basic arithmetic gives us a total shape factor of 18.36 meters.
Now we just take that 18.36 meters, plug it back into our super simple equation, multiply it by the fireclay's thermal conductivity and our 450-degree temperature difference, and boom, 8.592 kilowatts of heat lost. Seriously, in just a few lines of basic multiplication, we just solved a highly complex 3D heat transfer problem. That is exactly why this shortcut is such a massive game changer in the field.
And this works across totally different scenarios too. Using that exact same method, just swapping out the shape factor formula, we can easily calculate that a 15-centimeter diameter pipe buried in the earth loses 859.6 watts of heat. The geometry completely changes, but the elegant logic remains exactly the same.
Finally, Section 6. Finite differences are numerical methods.
Okay, so what happens when your design has wildly irregular boundaries, or maybe complex heat generation that those shape factor tables just don't cover? That is when we bring in the heavy computational artillery. With the finite difference method, we literally digitize the object. We divide the whole body into a grid of equal x and y increments. Wherever those grid lines cross, we assign tiny nodal points. Then, we replace the whole idea of a continuous temperature field with a network of fictitious heat-conducting rods connecting all these nodes. By assuming the net steady-state heat flow into any node is 0, we can set up an algebraic equation for every single point on the grid. It creates this massive web of simultaneous equations that modern computers can crunch in fractions of a second, giving us an incredibly accurate temperature map.
So, when it comes down to it, a thermal engineer today relies on 2 primary highly practical tools for multidimensional heat conduction. On one hand, you have shape factors. They're quick, they're perfect for standard shapes, and they offer a brilliant analytical shortcut for rapid estimates. On the other hand, you have numerical methods, absolutely perfect for highly complex shapes, relying on dense nodal grids and powered by heavy computational software.
We've journeyed all the way from the foundational calculus of the Laplace equation through the practical genius of shape factors and finally arrived at the digital frontier of nodal grids. It's really an incredible evolution of problem solving. So I'll leave you with this. Whether you're pulling a quick shape factor shortcut from a table or programming a vast numerical grid into your software, which method are you going to use to tame the heat in your next design? Thanks for joining me on this explainer, and keep questioning how the world works.